Right.
Okay, it's recording, but I don't know where it's recording to. But let's see here. Let me get back my presentation. Okay, good morning, everyone. This is the John Chappell Natural Philosophy Society Science Chat. It is July 28th, 2018. And we can be found on the naturalphilosophy.org website, and you can join us, and you can become a member or renew your membership. We have forums and our wiki, and we have Facebook. And we're doing a lot of things on social media. So please mark that you're interested on the Saturday morning video conference, or subscribe to our YouTube channel. Our members also have several YouTube channels that you can view. And we're also starting something we call Base Camp. And if you'd like to help volunteer for that, that would be great. Okay, so today we have Jeffrey Cook, and his topic is perpetual motion. So, Jeffrey, let me bring up your presentation here. All right, so take it away.
Good morning, everyone. Looks like we got 7 in here, so a small group. That's kind of cool. All right, so this whole topic is considered taboo most of the time, but I'm going to explore it a little bit different way, hopefully, because there are some facts to this study that actually are often misunderstood. So we're going to get into it. It's basically in terms of thermodynamic equilibrium and non-equilibrium thermodynamics. I'm also going to go into a subject that is taking a bit of a risk with it. It's just basically the planetary orbit. It's something that's well known and well studied, and so obviously any mistake with that easily stands out. But I think it would be very difficult to explain any of the perpetual motion without getting into that as well. Perpetual motion is also something that is well studied for hundreds of years and pretty largely understood to be nonsense. However, there are still people who look into it, even Nobel Prize laureates, and I believe the study is very warranted. And so we're going to get into that. You can change to the next slide here. I'm going to keep you busy because there's a lot of slides always with my presentations, so I'm just going to say next slide and just kind of click away. Slide. Here's the outline. All right, I'm going to start with a non-technical overview, a little bit of history. Next slide. Then I'm going to get into some math and theory. Next slide. And at the end, I'm just going to go over a few devices and a theoretical one I just came up with the other day because it's not one that I really believe in, but it's an issue to study and how you would approach and how you find flaws with a perpetual motion machine. In the early days of physics, back to Maxwell and before, physicists would challenge the other physicists by presenting purported perpetual motion machines and say, how does this not work? And it's good for the study of the physicists because they can learn more, especially if it's something completely new. Then they expand their understanding by finding flaws in a perpetual motion machine that's presented. If they can't find any flaws, then sometimes it's left hanging for a few decades, or somebody builds it if it's possible to build it, and then they produce it and it doesn't work, and they say, that's why it doesn't work, and then they have a better and deeper understanding of physics in general. So I do believe that the study is warranted even if none of them work, because I myself have found a number of things that do work. It's not perpetual motion, it's not free energy, but they were found in the search for it and study of it. So I only in the back of my mind believe it to be true and believe it to be possible, but I have to believe a little bit, otherwise it doesn't push me forward to keep exploring physics. Because every time you get an invention to not work, after you curse and throw your hands up in the air, you walk away and you come back and you go, all right, why didn't it work? And then when you do figure out why it didn't work, you now better understand nature. And so I believe that the study is warranted. So I'm going to present a theoretical or hypothetical propulsion motion mechanism, and then we can discuss of how, because at this point I can't think of how it wouldn't work. And so let's, next slide. All right, so this is a non-technical overview. Next slide. All right, so the history of perpetual motion, as far as goes back to recorded history, goes back to around the 8th century. A lot of them were shepherds and farmers and weren't, and most of them didn't draw or have paper means to draw. But there are some stories that there was a drawing as early as back there. And then definitely in the 1150 and 1230 and the centuries up until now, there's been a number. And these people were not crackpots, some of them may have been, but the inventor of the compass, he was a well-established inventor, and he's working on it too. So it's something that a lot of people have worked on over the years. Yes, they worked on it before the laws were better understood. But is my belief that there's still a lot to be understood with the laws of thermodynamics. So, but it's something.
Hey, you're cutting a little bit out on us.
Okay, my screensaver came up. What's that?
Where you're cutting out a little bit for us.
You're cutting out a little bit for me too. So, what's that?
Maybe our internet connections aren't great, but I'll let you know if there's a substantial interruption.
Okay, yeah, because when you speak, it's cutting out as well. So I don't know that it's from my end.
Well, how is the conference for the rest of the people? Well, if other people see interruptions, then
let me say a few things here. Well, first of all, you're only coming in one, but that could be my end. I guess I don't want you to miss anything. How do we fix it so that Franklin?
So right now you just cut out there for about 3 or 4 seconds. Are other people seeing that? Or is it just me?
Okay, I didn't hear anything you just said except 3 or 4 seconds.
Yeah, you just cut out for 3 or 4 seconds as well there, which wouldn't be good. Let me see here. Let's.
Yeah, well, I wasn't speaking at the moment, but I definitely hearing you cut out. I can't hear you at all.
Let's see here. Yeah, Mitch says Jeff's cutting out a little.
Yeah, I can hear that.
Intermittently. So yeah, it sounds like people are saying that they're seeing that as well.
Okay, somebody's mentioning minimizing the number of active cameras. So I think everyone's cutting out. I think it has something to do with the software.
Well, I can cut out my own camera. Let's see here.
Maybe just your audio. Because if the audio's cutting out.
Well, is that any better now that I've turned off my camera?
Except that I'll... Yeah, I'm hearing you every time you say something now. Yeah. Am I cutting out at all?
So far, it's okay.
All right, then let's continue then. Maybe that was all it took.
Okay, yeah. So everyone just turn off their camera except for Jeff. And you might have to turn off your camera if we still encounter some problems with that. But let's go back to the presentation. And let's go back to sharing. Okay, so we're ready to get back.
Okay. All right, next slide. All right, so I asked myself, what is our obsession with it? So people have been doing it for centuries. What is the obsession? I come up with 3 ideas. Go ahead, next slide. I think we're fascinated by the continuously rotating celestial bodies in the sky. We see the sun and the stars, the moon apparently keep moving around and around, and people are fascinated. They want to reproduce that on their table. That's one reason I can think of. Next slide. And here's the little animation. These guys got solar panels, and sun goes by, turns on a light. Lady comes out. Why you turn the light on? It's a pointless invention. Next slide. And then next slide again. All right, so I think there's a concept of eternity that all of nature strives for. Next slide. I'm sorry, I missed the slide.
There.
Yeah, so everything in nature tends to the path of least action and the path of least resistance. We prefer not to be pushed or moved, and all of nature operates that way. And so I think that's kind of the concept, or something that fascinates us with perpetual motion. If something is going on and on and on, we don't need to do any more work for it. So that's a drive of all nature and all humanity. Next slide. And I can think of one more. Next slide. Obviously, fame and fortune. Next slide. Because they, obviously, if you get the money, then, if you have that fame and fortune, it leads to greater amount of rest. So I can think of those 3 things. Why people are obsessed with it. It is something new, but it is something that's difficult. But I think those are the main things that make perpetual motion unique. So next slide. There's also a lot of hatred and ridicule associated with it, and I think a little bit too much, because it does prevent some warranted studies. Next slide. Here's Leonardo da Vinci's comments on it. O you seekers after perpetual motion, how many vain go and take your place with the alchemists? Basically, F off. That's essentially what he's saying. And he himself has studied it. And he became later frustrated with the concept of it, not believing it to be valid for the study. So there's some hatred. There's also a lot of modern hatred. I grabbed a bunch of comments off of YouTube videos. We could just skip through all the next slides. Well, show me the next slide, actually. Let's see what we got. Yeah, just go ahead and click the next 5 slides as I go. All right, so here you can read some of these. If you think this is real, you need to get your head checked. Everybody knows it's impossible. Of course, it's all BS. And this last one here, I'll hold up on the next slide, is I deleted the username. Guy has a lot of guns on his videos, and he's suggesting we just shoot it with perpetual motion instead of the invention. That's a lot of hatred for perpetual motion, something that's a long phenomenon. Okay, so I asked myself, why? Why do people hate it? And next slide. Frivolous efforts, everyone hates that. It's a big waste of time, and it's just something people naturally despise. Next slide. Well, we don't want to waste time. Life's too short, and when people see other people doing it and getting a lot of attention for it, if it's real or not real, people just resent that, and they don't like it, because they, in their mind, know that, obviously from the frauds, they know it's not to be true, and so they hate that aspect of it. I can think of that one. Next slide. Next slide. In the case of Leonardo da Vinci, some have tried, and when they got to the point where it's impossible, they quit. And next slide. And when they're like, anyone who quits anything they hate it usually more than anyone else. They hate what it reminds them of what they once were. So like a smoker who hates smoke more than, an ex-smoker hates smoking more than just about anyone, the smell of it, everything. It's the same thing with this, because they have gone through it, they've convinced themselves that it's nonsense, and anyone reminding them of it. I can think of that one. Next slide. And next. So, fraud, yeah, so everyone hates that. Next slide. Alright, so somebody who does present something that's they know in the back of their mind is fake and they're just trying to make a buck. I don't know how you would make any money off of perpetual motion machine if it was, especially if it was not true. But there actually have been some, I think I've seen some people where they were trying for something, just flipping through some videos online. They were trying, it didn't work, and they anyway presented it to be real somehow, faked it. And I know because I've reproduced some of them and exactly as it was, and it's nonsense. It's simply not true, nor it couldn't work, and so they're not taking money off of it, but that's about a large amount of waste of time for a person trying to replicate it, to believe it. They get roped into it. Throw a lot of people hate that as well. I could think of 3 reasons why people hate it. Can't think of any more. All right, next slide. Next. All right, but have there been any successful slides? Now, John Warfield, who some of you know, sent me a video a while back, and of a guy, and I have heard of this before, but I didn't actually see this video. So there's a video link at the bottom if any of you want to write it down while I'm discussing it and watch it later. I didn't want to put videos in this presentation because I'm not sure if they'd work. We're in new software and everything. So, but essentially, a guy, Aldo Costa, I don't know if any of you heard of him, came up with an invention. He was a very quiet, private individual, and he built one. And this Eric, I don't remember his last name offhand. He's an actor, and he's a self-proclaimed skeptic, and he has offered to anyone $10,000 prize if you present a perpetual motion machine. And so Aldo Costa, after he had built his, and he had been working on it for decades, variations of it, he built it and sent him an email. And there's a video on this whole situation. Next slide. So when Eric gets to his house and he sees this large thing moving on its own, it's enormous, it's bigger, taller than the house. He's fascinated with it, and you can watch the video and you see that he is amazed by it actually, and it is turning. It's not turning fast, but it is turning, and he likes the construction of it. He saw there's nothing fraudulent about it, and when Aldo asks for the money, this is what he said. Next slide. He's like, even though it's continuously moving, I cannot see it as a source of external energy. That's not what he proposed. He proposed a perpetual motion machine, not a free energy device. So, to me, as I'm going to get into here, they're 2 very different things. In fact, I don't really see how the 2 can even be one and the same. It gets very complicated. But he didn't ask for a external energy source. He asked for a perpetual motion machine, which it does seem he built. It does seem to work, and didn't give him the money. So now where's the fraud in this? Next slide. So he sends out this request to, hey, give me your perpetual motion machine. I'd love to see it. I'll give you $10,000. Doesn't follow through with his end of the deal, and then it raises the question to other people out there. Next slide. What part of the obsession is worth it then? So I don't believe fame and fortune is possible from ever building it, because no one's ever heard of Aldo Costa, and I do believe it to be true. It's there, anyone can go look at it. So fame and fortune's out. Next slide. Because if it is free energy, how do you ever get money for it? It's free. So it certainly can't get money off of something that's free. Of course, water's free, we charge for it, but just cleaning and other things go with it. But in general, I don't see ever any money being made out of it. And I don't really think of any fame ever being made out of it either, except maybe for hundreds of years, which you're never going to live to see, which is the next point. Next slide. If concept of eternity is something people are interested in, that's pointless too, because you're never going to live long enough to see if the machine ever does stop. So that's not really, to me, not worth it either. I'm interested in the last one. Next slide. I think this is the only thing that makes the obsession worth it, is we just need it to be continuous for some amount of time. It doesn't matter if it stops in 1 billion years. It doesn't matter if it stops in an hour. If something cycles on its own for 5 seconds, that's neat. That's fascinating, because that's exactly what we're talking about. Where is the energy coming from? It's continuous. There's two definitions for the word perpetual. There's one that's eternal, and the other is continuous. So we want it self-sustained, and that to me is good enough, because the planetary bodies, the sun, the moon, they may not be eternal. An asteroid could come and change off the trajectory. There's a number of things that can happen. Some people think they're just going to slow down on their own. Whatever the reason, it doesn't need to be eternal. It just needs to cycle, like we've been seeing since humanity's been on this earth. If we had something like that, to me that is fascinating enough. So for me, that other invention he has is everything I would expect from a perpetual motion machine. I don't care if the wind one day slows it down. I care, does it turn on its own, and how does it do that? So next slide. All right, so this is what I'm looking for on my tabletop. This is what I would be interested in. Sustained repetition without further input. I believe this is the original and truest meaning of the word perpetual motion. Next slide. And how do I see them as two different things? Next slide. So perpetual motion just means it needs to continue in motion. It's self-sustained for some amount of time. And obviously, the longer, the more believable. You know it's not momentum, just moving along. Next slide. Free energy would have to have that and then do something else. You'd have to be able to have this moving planetary body and extract it. Is that possible? I think so, because the moon seems to be rotating around the Earth perpetually. You know, I don't know if it will forever, but it seems to be. And yet the Earth does extract energy off of that. It's moving the oceans, which is a huge mass, and it has a huge amount of energy when it does that. So the tides is basically extracting energy from the moon, and it's the motion of the moon. All right, so next slide. All right, so I'm not interested in free energy at this point. I am interested in it, but I think that this study is going to be perpetual motion. I'm fascinated along. Does it continue? Is there some mechanism that causes something to continue in motion over time, indefinitely? Let's not say forever or eternally, just over indefinitely. We don't know when it's going to stop. Next slide. And I believe that continuation is enough, because that is what people are saying the laws of thermodynamics describes as being impossible. But we will explore all of the exceptions to that as we go on. Next slide. All right, so part 2. When you get into the math, what does it look like if something would? Mathematically, what would it mean if something is moving continuously without further force? Next slide. All right, so I'm going to get into here how perpetual motion is not free energy. We've got Newton's first law of motion. So the sum of... Oh, my screensaver keeps going out. The sum of the forces acting on a body equals 0 if and only if the rate of change of velocity equals 0. So this looks to most people as having the singular meaning. But, and then it actually can describe three different systems. It can describe a big heavy weight sitting on the ground, which has no force because it's not moving. It has 0 potential energy and it has 0 kinetic energy. Then you can also describe lifting a heavy weight above your head. Then it has, and if you're holding it still, it has no kinetic energy, but it does have potential energy. And then we have the third, which would be the perpetual motion concept, is where it is continuing in motion at a steady velocity, and it also has potential, so it has kinetic energy, but also has potential energy, because if something gets in the way or smacks into it, then the energy is transferred. So at that point, in the same equation, you have three forms of energy. But the last one, you have 2 energies. One that's potential and one that's kinetic. That suggests 2 different forces. Now, you look at the equation, you say, I'm hearing a lot of noise. Is that my feedback?
I'm hearing that as well. Did someone not mute or come on to the conference?
Somebody's TV or something, I don't know. Well, I'll continue. I'm not concerned about it at this point. All right, let's stay on this slide. All right, so this is the standard equation most often describes Newton's first law, but I think there's a different way to look at it. We have the changing velocity over the changing time. I think it might be better to describe in many situations, orbits particular, a changing velocity times a changing frequency. And the reason is because there's no difference between gravitational orbit and elliptical harmonic motion. And harmonic motion is described in terms of frequency. So if the rate would diminish to 0, then you would hear in this equation you get the force diminished to 0. But if the time and the denominator reduces to 0, it has no meaning. So it's undefined, right? So I think the better way to describe this would be a change of velocity times a change of frequency, the rate of the change. And either way, how you look at it, both can be worked on. But the study is going to be an acceleration that decays to a velocity. That's what most of this discussion is going to talk about. When you have an acceleration decay to a velocity, and that velocity is greater than 0, you still have zero energy transfer. You have kinetic energy. The question is, where does that come from? But from the work energy theorem, which we have here, if the net work done on a body is 0, it means the kinetic energy of the body is going to stay the same, which means that it maintains a constant speed. So there is no energy being applied to that moving mass anymore from if it's at a steady velocity. And the only way you can describe that in terms of Newton's first law of motion is in terms of elliptical harmonic motion, which would then involve a changing frequency that would eventually reduce to 0. 1. All right, so let's or it'd be 0 in this case, in the equation. But can we go to the next slide? All right, so the force you exert on a stationary body, such as this guy lifting the weight, gives the body 0 energy, as displacement is 0. It's not moving. No work is being done in the body. It does have potential energy. So Newton's first law of motion can describe the force 0 with potential energy, or no potential energy, or potential energy with kinetic energy. In this case, we would have potential energy without kinetic energy, and 0 work would be the result. Next slide. Perpetual motion would be the same. It would be 0 work being applied from the sun to these planets if it's perpetual, and because it has some force, but the force it's not changing its displacement. Yes, it's moving to or from, and we're going to get into that. But in general, it's maintaining a constant speed, not a constant velocity. Velocity would be the change of the Earth as it gets near to the sun. It's going to speed up as it gets a little bit further away. It's going to slow down. That would be a change in the velocity. Does it go around one time every 365 days? And does it do that the next year and the next year? That's speed. If it has a constant speed, there is no work being done from onto the Earth, all right, or in these celestial bodies. All right, next slide. All right, so some of these Physics 101 facts are still debated. And so I asked a question to an astrophysicist, and I took several responses and combined it as one person. So I asked, will the Earth fall into the sun? And the astrophysicist said, no, because it's beyond its escape velocity. All right, then, so perpetual motion exists. No, the Earth's orbit is slowing due to tidal bulges, just like the moon, due to friction. And I say, so, well, I don't think there's friction in space. I'll get into that later, but okay, so then it'll stop. And he says, well, yeah, it'll stop if it's constantly slowing due to tidal bulges. And I say again, if it stops, then it'll be slower than its escape it'll crash into the sun. So the question I raise is, could it be converging to a steady velocity greater than the escape velocity? And if so, wouldn't that be perpetual motion? Next slide. Here's an example. The question, and I've seen there's some discussions out there on this, will Voyager 2 and these other probes that we send in outer space return to the sun? All right, so basically, this is where a pointer would be useful. If you direct your attention to the center orbit where the probe is launched, I'm assuming that's the orbit around the sun of the Earth. As is launched, let's imagine it's perfectly circular, the orbit. At least the orbit of the Earth is not perfectly circular, but let's use a perfectly circular frame of reference. And it spirals outward using gravitational assist, and it has curvature. And as it gets past the last planetary body that's going to use gravitational assist, it gets further and further away, and you see the lower it slows from 17 kilometers per second to 15 kilometers per second, and it's slowing infinitely. But is it slowing to a stop infinitely, or is it converging to 14 kilometers per second, or 13, or something else greater than 0? Because if it does slow down to a stop somewhere out there, then it's going to return. And then the meaning of escape velocity has to be better understood as basically we have the escape velocity to send something from one orbit to another. And if it doesn't go in another orbit, then it's going to return. Or we consider the alternative is that it is going to keep going in a straight line like the astrophysicists believe. As it goes further and further away, the trajectory starts to straighten out. The curvature is due to acceleration, which is due to, or deceleration, which is due to force. So as it starts to get further and further away from the force of any other planetary body, it starts to straighten out and continue down or converge down to a constant velocity. Next slide. So there is no friction in space. People are often saying, "Oh, there's interstellar dust out there, and that's going to cause friction on it." That's not really friction, actually. The friction is a non-conservative force, and we're talking more of bombardment of particles. So we have to look at it in terms of this. So if, like billiard balls, if it hits it, the billiard ball is going to move in the opposite direction. But we have to look at what's the probability of it hitting this. What's the probability of it hitting a giant star out there? What's the probability of it hitting an asteroid or a grain of sand? No one knows, because no one knows what's out there. So obviously the odds increase the larger the object, but space is very big, and so an object is very small depending on the trajectory. So then you can have a big cloud, more density of dust, then you have a higher probability of that dust slowing the probe in space. But then you have to consider, what's the probability of particle dust being out there anyways? If it's not stationary, it's moving. And if it's moving, it was probably expelled from the solar system itself, probably from the sun, and it's probably moving in the opposite direction of the sun, and therefore it's moving the same direction as the probe. So two runners running next to each other are never going to bump into each other if one's going faster than the other. Now, I got to consider also, is it coming towards the sun? And if it's coming towards the sun, does it have the same trajectory? Then you could think, well, it could. But here's the biggest question. Where is the concentration of planetary dust, matter, anything? It's going to be closer to the sun. Because as you get further out, that orbit becomes larger and larger and larger, which is probably likely to say, if it was going to hit anything to slow it down, it would have hit it already. Now, there are some estimations of how much planetary dust is out there. We do know that the escape velocity of it being launched is not large enough to get it out of the galaxy, but the question is, does it have enough to leave the sun? And if it does, then we have an issue of perpetual motion, at least as far as I can see it. So it's not going to be slowed to a stop, and I'll show you why. Next slide, please. So when things are left to chance, such as this, no one knows what's out there except in the exact path, and anyone claiming they do is confusing themselves and confusing the issue. So my guess is as good as yours, 50-50. So if the probability of 50-50, then we send 100 out there, 50 get slowed down, and the other 50 go forward, then that 50 have perpetual motion, and the study of perpetual motion is warranted. If there's a 1 in a billion chance, it's still warranted. Now, if there's 0 chance that it will go on forever, that something's going to slow it down to a stop, then they have to prove how there could be a greater density of dust or something out there slowing it from the sun, how it must be moving to the sun or towards the object, because again, the dust is not just floating out there, it's moving at some velocity, most likely as fast or faster than the probe itself. And they would have to also prove the probability of the trajectory, because space is very, very big, and it keeps spreading out the further it gets. Things start getting further and further apart. And so we have to show why, if there's so much dust out there that's going to stop it over time, did it not stop it already when there's so much more things it could have run into asteroids, which are obviously very spread apart, but less spread apart than something beyond our solar system. Okay, and next slide. So if there were perpetual motion, and if that Voyager 2 will continue on forever, what would it look like mathematically? So you can do this on the small scale, which we're going to move. I'm going to do some quantum physics here. I'm just going to breeze over it. Considering the Boltzmann distribution for the fractional number of particles, which is the initial quantity over the changing quantity, occupying a set of states n possessing energy E sub n, perpetual motion would give that ratio equal to 1. So in the third equality, we have the degeneracy factor times the exponent expression here, and then the partition function z. And that equals the ratio, which also I have 1 over chi of t. I'm going to get into that in a second. Basically, that would equal 1, such that the degeneracy factor, which is g sub n, equals 1, and would also be equal to the partition function. Now, all of this is actually standard physics, so I'm not going to get into it. You can go look this up. I am going to go a little bit on the degeneracy factor for a second. But it is basically the total number of particles. It's the number of levels having energy E sub n. And when it's 1, it means it's non-degenerate. And it's also in an asymmetric state. So if you have 2 energy levels or 2 energy that share the same, it's like a teeter-totter, it's balanced. And 3, if you have the third one in the middle, it's going to be balanced. Or, so it's not only odds and evens. But 1, it's asymmetric, and asymmetric states do not collapse on their own. They are self-sustaining. Get into that in a second. Otherwise, no matter would hold together. Next slide. And this is pretty well understood in terms of ground states and zero-point energy. We're going to get into that in a second. So, a decaying quantity. Let's consider the decaying quantity acceleration. And it's going to decay to velocity. So a quantity decays infinitely to a value greater than 0 when the limit of its rate of change is 1. So if the initial starting point is eventually asymptotic to the change, so that somewhere out in infinity it returns to the same value, the ratio was 1. And in the equality, the top equation here, the top equality over to the right, I have put this into, and it's not hard to derive, I've put it into in terms of harmonic motion. So it's a big equation, cosines and sines, but actually it's very useful because here, right before that, you have e to the power of minus st. S would be the decay constant or propagation constant, depending on whatever you're talking about. I just call it s. And then e to the power minus s times time is equal to this other. What I've done is I break s and make it a complex quantity or a vector quantity, and I describe it in terms of its real and imaginary parts. Alpha is the is the real part of S, beta is the imaginary part. And then you can describe it in terms of propagation of electromagnetic waves in space, any form of harmonic motion, elliptical harmonic motion, whatever. But this is what is going to happen, and you can calculate the decay of this limit cycle. We're going to call x of t a limit cycle. It's a position that changes over time. And the second equation at the bottom is essentially, I wish I had my pointer here. Okay, so we have ways to calculate it based on a change of angle, which is theta, and based on the attenuation constant or the real or imaginary parts of the decay constant. Okay, what you can come up with is the derivative of theta becomes the inverse. This is it for perpetual motion specifically. The derivative of theta equals the inverse of the limit cycle or the changing position, such that then the derivative of the angle becomes the inverse of the inner circular radius, and I'll show you the geometric proof of this in a second. So basically 1/2 of the inverse of the sine of theta. The limit, what this means in the end is that the for perpetual motion to be possible of any decaying quantity, something that doesn't decay, is the initial value, so its position, must be equal to negative reciprocal of the decay constant, s. So x of 0 equals 1 divided by minus s. That will mathematically have to work, and I'll show you why. You're not going to get around that for perpetual motion. Next slide, please. Alright, so I see when I looked at the Voyager 2, I have an orbit, a circular orbit, a frame of reference that Voyager 2 is going to leave in a spiral motion out. So I have two limit cycles with this. A limit cycle, and I'll get into what limit cycles are in just a second, in case people don't know what that is. We're talking about decay of anything. Decay of acceleration, decay of matter, decay of the propagation of amplitude of light traveling through a solid medium, exponential decay of any form. So exponential decay of force. Okay? So it doesn't matter what it is, I just call it x. But we have two limit cycles, and I'm going to have a geometric proof, and we're going to show how that Voyager 2 and the orbit, how you can describe it in terms of a limit cycle. Just in the same way that you can describe gravitational orbits in terms of elliptical harmonic motion. A limit cycle is the way you mathematically solve for harmonic motion. Alright, so we have limit cycle x of t. Alright, that's the position of something anywhere at any second. And the position with respect to an angle. So the limit cycle on the right, x of the angle sub t, is a perfectly circular orbit. That is the frame of reference that the spiral trajectory leaves away. And so let's let the limit cycle be defined as such, which is the first equation. And this limit cycle can be accelerated for any vector quantity. And in this case, we'll consider it to be the decaying acceleration of Voyager 2. Hold on. Alright. And then we're going to consider the other one defined as this. And the limit cycle can be acceleration for the other, but in this case we're going to consider it to be the acceleration of a perfectly symmetric orbit. So as a planet is orbiting something, it has acceleration, it can be calculated. Perfectly circular in the second limit cycle. And so if you plop these equations into mathematics or anything else, it'll easily show you that it has, neither of these have any roots, the value is never a zero, and both are periodic. The two different periods are shown below. The period of the limit cycle, the spiral limit cycle, is minus 2 pi divided by the imaginary part of the decay constant, and the period of the circular orbit is simply 2 pi. It's circular. Next slide, please. So what is a limit cycle? A limit cycle is a closed trajectory in phase space having the property that at least one other trajectory spirals into it, either as time approaches infinity or as time approaches negative infinity. Limit cycles have been used to model the behavior of a great many real-world oscillatory systems. This picture here is the limit cycle of a Van der Pol oscillator, and I worked with different oscillators similar, and also a changing orbit of Earth can also be described in terms of a limit cycle. Let's go to the next slide. So, in the case of, we talk about trajectory and self-sustaining systems, all right, and limit cycles. And self-sustaining leads to the perpetual motion, okay? And trajectory actually comes into play as well. In the case where all neighboring trajectories approach the limit cycle, this is standard limit cycle discussion here. This is nothing new at this point. In case where all neighboring trajectories approach the limit cycle as time approaches infinity, it's called stable or attractive limit cycle. All right, so all of those trajectories come together as it approaches infinity. You can also describe it another way, going from infinity all the way to zero, coming together, and it has a different type of stability. If instead all neighboring trajectories approach it as time approaches negative infinity, then this is considered an unstable limit cycle. If there is a neighboring trajectory which spirals into the limit as time approaches infinity, and another which spirals into it as time approaches negative infinity, then it's a stable, semi-stable limit cycle. Now I understand a lot of you have never studied limit cycles, but it's a fascinating subject, and if you're going to study planetary objects or most of physics, it's going to come up somewhere, or it should anyway. So this is something I think everyone should understand. Stable limit cycles imply sustained oscillations, and the closed trajectory describes perfect periodic behavior of the system, and small perturbation from this closed trajectory causes the system to return to it, making the system stick to the limit cycle. This is not theory. This is what people... Who's talking there in the background? Pal? Who's that?
Well, let's see if we can go find him and put him here.
Yeah. I think that's him.
Let's see here. Okay, that should have muted everyone except for you and me. So I think I got ready.
I don't hear him anymore, so yeah, I think so.
All right, back to our regularly scheduled presentation. Okay, should go all the way. No, okay, there we go.
Cool. All right. So this last statement is if you understand limit cycles, then you'll understand why the dust in outer space will not affect the orbit, because if it is a stable limit cycle, then it's a self-sustained oscillation, and any small distortion of the path is not going to cause it to diverge, mathematically or physically. It will return to it. So the system sticks to the limit cycle. It's well understood mathematically, but you'd speak with certain astrophysicists and they think of it in terms of common sense, that if it hits dust over time, it's going to stop. That's not necessarily the case, actually, in terms of limit cycles, even if you're talking about a fraction of an orbit, which is basically a curve due to the force of gravity, and it never makes it around. Even if it's that, it's still, you got limit cycle at play, and nothing's going to distort it from its trajectory, except something that's, obviously we're going to get into forces being greater. So, let's continue. Sam, why am I calling this perpetual motion? It's a self-sustained system, that's why. Stable system example. Okay, so here's a stable system example. You have an increased, this is actually taken off of an invention that I'm going to show you. So actually I've been studying for a couple of years. I think the last time I did a presentation here was 4 years ago, and I mentioned I was working on something. I did discover how to do it about 2 years ago, and I have some pretty good math tied to it. So basically, as a magnet approaches this metal sheet, it accelerates, and it approaches a gap. So you see this rise in the on the graph, and that's about a quarter of a Newton there. And And then when it reaches the gap, it is resistive. It meets a repelling force back. We'll get to it in a second. Drops it down, but it actually does not slow to a stop. It just slows to a constant. And if I repeat it, it basically continues on forward. So it's basically a little hiccup. That's an example of a stable system. Now, I'll get into that. I don't get into that too much. I'm not saying I have a perpetual motion machine, but I want to show it to you and then to discuss it. So go ahead. Next slide to me. So, a semi-stable system. Any electrical engineers out there are going to look at this net force, the brown line, and say, that looks like a battery discharge. So, essentially, forget the other two lines at the second and just look at it. You basically have the curve of a battery discharge over time. If you think of this in terms of voltage and a constant load, it starts to decay slowly, and then once it meets a certain point, let's say 8 hours, depending on the battery, whatever it is, the voltage drops off quickly. This is a example of a semi-stable system. All right, this can be described in terms of force too, which is where this equation came. So you have the force out in the body. So you push a body, it accelerates, and then decelerates over time and eventually stops. Now, there are equations with the force of the vacuum. Obviously, they're disputable, but what you have is anything that is moving, anything at all, is going to interact with the vacuum of space, because vacuum of space is anywhere at any given time. And as that increases over time, if it does match the force, and once it becomes equal to the net force, the whole system collapses. And the reason for that is because then it's no longer an asymmetric system. And so it's no longer a symmetric, no longer asymmetric system. Symmetric systems collapse. They have a degeneracy greater than 1. So this is what a graph of a semi-stable system would look like. And you can use this graph in terms of electrical potential, force, acceleration. It's all going to work the same. Anything that decays exponentially over time. And these equations here that led to this are simply exponential decay equations. All right, next slide. And so was the other one, the previous. Here's an example of using the same exponential equations, an example of an unstable system. So you don't see the force on the body graph because it's covered up by the force of the vacuum graph. They have the same exact value. So it's a symmetric system, and it's unstable, and it quickly collapses. Once the amount of energy is expelled, it quickly collapses. Next slide. So these are limit cycles described in terms of exponential decay. Geometric representation, here we go. So we're going to plot a complex value. This S could be acceleration, it could be any vector quantity, it could even be, if you're discussing the exponential decay of matter, then it would be a positive real number, but that still can be expressed on an imaginary plane. Just consider its imaginary part being equal to 0. So we're going to plot that point. We see where theta comes in, as we were discussing before. Next slide. And we're going to represent time geometrically, being radial around a certain radius. And the radius is the inverse of the imaginary part of S. We can let it be anything, because we're setting the premise. And time would be basically not the points on that circle, but the length of the arc. Next slide. So the limit cycle is anything that changes in position. So we're going to let that circular limit cycle be symmetric. We know it's symmetric when the limit chi of t is 1. At least if you go through the equations, you put it in, it comes out that way. It has to be. So if we let can I skip this? I'll go through it quickly. If we let time be theta divided by, as we were discussing, theta divided by the imaginary part of S, then that circular orbit becomes modular, radial centered on 0, with right or left-handedness. So the values cause it to cycle around that 0. And then, this is a mouthful. It helps to have the picture up at the same time, but I'm just going to read it so you understand. That circle becomes internally tangent to the basis of a plane section of a double-sided cone circumscribed to T, such that this equality occurs. Thus, when taking that limit cycle over increasing magnitude values, so 0, 1, 2, it rotates clockwise around that radius, And when you take a decreasing magnitudes from infinity to 0 or 1 to 0, anything decreasing, it rotates counterclockwise. And the reason is because this circle is periodic in 2 pi, circular. I will show you what it looks like, the geometric proof. Next slide. Oh, it's not the slide. Okay. Here you can also describe it in terms of improper integrals. All of these equations basically says it sums to the circumference of a circle. That's essentially what all of this is saying. Let's get on to the next one. Next slide.
Oops, sorry about that.
Did we go backwards? Yeah, that's okay. So here's the geometric proof. We are talking about two tangent, internally tangent to the circumscribed circle. Here's basically how it all plays out. Looks like we're talking about. I know this is almost impossible to follow at this point, but let me try to get you up here. What we're basically doing is you see these values of here's this position, x of theta, and there's a 1 under. If you can see, my image is pretty small on my screen. And you see 2 where it is at point 2, where it is at 3. And it starts to appear, you plug these values into the equation, these arguments into the equation at different times. It shows where the position of it is at any given time. As it increases over time, it creates the circumference of the circle. So that's our mathematical proof of that limit cycle. Now we're going to combine this with the other limit cycle. Next slide. There's a geometric representation of that. So we're going to then do the same thing with this other limit cycle, which is the spiral limit cycle. It's very similar, so I'm not going to go over all this, but it spirals counterclockwise and then for ascending and descending. Next slide, we can represent it in an integral form. And here you have both of them represented geometrically. So here you see the spiral. Now you can describe this. This is the spiral. You can now start to look at this. This is the geometric. It has no, it's purely numerical analysis, but you can apply this to the trajectory of Voyager 2 and the orbit, the circular frame of reference orbit. And you see as it looks like the spiral is getting smaller and smaller and smaller, but that can be described in terms of distance. Okay, so here's the geometric proof. This is how they are connected. And you look, there are 2 limit cycles that begin at the same spot, x of 0. They connect right there where that dot is in the upper left-hand corner, x of 0. That is where they both begin, and they diverge from each other. So we're talking about 2 limit cycles interacting. We can describe the orbits and the escape velocity in terms of geometric, or we can do it in terms of velocity, force. All of this is going to fit into these equations because it all has to do with exponential equations. And we know it's going to be valid because we can, if we argue that this geometric representation is true, you know, geometric proofs are neat. They're obvious. It's like Newton's first law of motion is obvious. If something at rest is going to stay at rest. That's what geometric proofs do too. So you got to have to see that all of this ties in neatly. So that's locked in. Now let's apply it to something that's a little bit more controversial. Next slide. All right, so here we have basically the same thing. It's not a perfect spiral, but we can envision the perfect spiral, and we can do the math to connect the dots. All right, this is how it's applied. And we can consider x to be position, or we can consider x to be acceleration. And either way, it's going to have the same values, or it's going to be represented in a similar way. Next slide. Now, the question is, why does Newton's first law occur? It was a qualitative law. It was something that he knew would be extremely obvious to anyone. Oh, sure, the anvil is going to sit there on the ground until something moves it out of the way. Of course, this is a law of nature. And then he used it to move on to the second, which were quantitative laws. But now the Maxwell and Euler and others have come along, and they've clarified these forces and fields in ways that Newton didn't, nor did he have any premise to work from in the beginning. We now can look back and say, well, we know why Newton's first law occurs. An object remains at rest because the sum of forces keeping at rest are greater than the sum of forces attempting to put it in motion. But can that wolf blow that anvil with the same amount of force using different means? And the answer is yes. You can use leverage. So let's imagine those as dust particles in space. Is it enough to move it? Is it enough to slow it? No. But with right leverage, you can use that force and magnify it with mechanical advantage. Next slide. Here's something from the cathedral here in Toledo where I live. If you look at this image, they have like a 7-foot tall piece of metal, and it's over a baptismal font, and it's extremely heavy. And you can lift it with your pinky. So the reason is, of course, because it's got these pulleys that are all stretched all the way to the top. It distributes that leverage through the length of the cables, and you lift this extremely heavy weight with the force of your pinky. So I've been there and done that. It's kind of neat, cool engineering. Why, I don't know, but in any case, it's very. So we can move that anvil with minimal amount of force at the same cost. The cost is distributed over distance and leverage. Next, we know this, right? So this is common sense. But let's apply it to things that we don't fully understand or know yet. So why does Newton's first law occur in terms of moving motion? Because the sum of the forces attempting to bring it to rest are less than the sum of the forces that put it in motion in the first place. Right? Common sense. You would think. It goes further. Next slide. Why Newton's first law occurs. All right, so we're going to describe it in terms of a changing frequency. The rate of change of velocity will cancel out over time, but the net input velocity. Now this is obviously theoretical. This is not what Newton said. The net input velocity will remain constant as it has already occurred in the past. Just like the force was there, that happened in the past. We're talking about something changing over time. And then, so that's can theoretically be constant with a changing rate over time that diminishes to zero, or diminishes to to zero. So if the frequency, the rate of change of that velocity decays exponentially, but the velocity is constant, the force will end up being zero, yet it'll still continue to move. Next slide. So I'm going to just raise questions, and I like the challenges of discussing some of these things, because there's so many different ways to say, no, that couldn't happen because of this, and I like that. But here's the questions. Is perpetual motion possible in general? Well, is the velocity of a ray of light going to slow to a stop one day? And isn't a wave of light a self-sustaining system? Now, some in this believe in the ether, and so that light maybe is not a self-sustaining system, that it has something to do with other mechanisms that I don't understand. But is the system itself showing the propagation of light a self-sustaining system? And is the velocity going to slow? That's not typical of what we see light do. So if light is different than matter, then how would we describe a universe where there's no matter, it all decayed, all stopped moving, and light is the only thing left moving? Well, at that point, how would you describe radiation without matter to interact with it? Because what we define as light is the reflection off of matter. We can't detect radiation. It doesn't exist if we can't detect it. Or it leads to very strange theories like dark matter and things of this nature. But I want to ask, how does matter behave differently than light? If light is going to go on perpetually, if the sun burns out, that light is still traveling in space, for who knows how long. Is it not eternal? What could slow it? And is electromagnetic radiation exempt from the laws of thermodynamics? I ask these questions because I don't believe that they can be, but let's look to see what we do. Next slide. So let's just consider quantum states. What about these that have zero degeneracy? Asymmetric systems are non-degenerate. So two or more different states in a quantum mechanical system are said to be degenerate if they give the same value of energy upon measurement. In classical mechanics, this would be described as we were discussing with the trajectory of Voyager, in terms of two different possible trajectories corresponding to the same energy. If we can describe it essentially if it's non-degenerate, and the ground state is always non-degenerate. So that brings in 0-point energy. This brings in the vacuum energy. There's something present in every stable system, and degeneracy is always equal to 1. So we definitely know certain systems seem to have this as a part of their origin. But what about something, a matter that behaves like light, that is constantly changing in time and space, and then become time crystals? Next slide. What are time crystals? It's a structure that repeats in time and space. I really don't like the name, but I think it started out as a mathematical challenge with these physicists, and one of them was a Nobel Prize laureate, and actually it's been observed. It is now a proven real fact of nature that matter can just show, how would you say it? I don't want to say perpetual motion, but that's kind of where they're getting at, all right? So it's a type of non-equilibrium matter, a form of matter proposed in 2012, fairly recently, and it was first observed last year. So this is, now we see matter starting to look a lot like light, with it having some properties that suggest perpetuity. Next slide, please. So what we're talking about are two different types of systems, all right? Thermodynamic equilibrium and non-equilibrium thermodynamics. Time crystals would be non-equilibrium. Most of the machines in our world that we build are thermodynamic in equilibrium. They're perfectly symmetric, circular. They are machines that eventually will stop. But I'm going to show you something else. Hold on. Next slide. Very importantly, the laws of thermodynamics govern systems only in thermodynamic equilibrium. Slide. Next slide. A system in thermodynamic equilibrium cannot experience perpetual motion according to these long-held interpretations of the laws, right? So we've seen these machines simply don't work. Next slide. Law gives nothing other than rough approximations in certain remote conditions to non-equilibrium thermodynamics. So it's very difficult to apply the rate of change entropy to non-equilibrium thermodynamics. And if you're doing research on this, almost impossible. You can get these certain conditions. Oh yeah, I have the approximation. The entropy is going to be here, this value at this point. So we definitely know entropy is at play, but we cannot apply the laws of thermodynamics to these systems because they're not in equilibrium. And really, physicists who understand this will agree with this. This is not new. Next slide. So, non-equilibrium thermodynamics is the study of systems in flux, such as the acceleration and deceleration of celestial bodies and their elliptical orbits. Next slide. We're looking for change. And most systems in nature are non-equilibrium thermodynamic systems. Our life is this. It's non-equilibrium thermodynamic system. We cannot apply entropy in the same way. We will eventually one day die and decay, but we also are increasing our negative entropy over time every time we eat, and that's what life is. It can be defined of. It's not a stable system, it's a semi-stable system. So life is a natural process. And so if there's perpetual motion, we're going to be discussing it in terms of non-equilibrium thermodynamic systems only. All other systems will decay with the defined laws of physics, the others, because we can't even begin to approximate how entropy can be applied. Next slide. So some will ask, well, the moon's spin reduced to 0, so then it's fair to assume that the orbits will reduce to 0 too over time. Next slide. There's a difference between spin and rotation, particularly, and we know this, but particularly in terms of gravity. Spin has one force acting on it. That was the force that put it in motion. Rotation has two forces, the force that put it in motion and the force of gravity as it changes in location. Next slide. So let's just quickly look through these. Next slide. Do next slide 3 times. Okay. So here's the difference of the spin and rotation. Very obvious. It's one's around the center of point. An object around the center of point of another. Okay. So so next slide, we got one more I want to show on this. Yeah. So a spinning mass is a system in thermodynamic equilibrium. It's circular. It's going around. It's subject to the laws of thermodynamics. Next slide. The orbiting mass is a system in thermodynamic non-equilibrium because it does speed up and slow down. There's 2 forces, the one that put it in motion and the one that brings it to and fro. So as the force changes, as the Earth gets closer to the Sun, it accelerates. And so it's a different force than the one that put it in motion. The one that put it in motion is past tense. So next slide. So the spin versus rotation is different. Now, I get this. This is why I believe in perpetual motion. I believe it's not only possible, but commonplace in nature, because signals, and I saw some of the discussion about impulses, they can travel faster than the speed of light. So if these guys are tug-of-warring and they're holding on to the rope and they give a little tug, they feel it instantly. Now, we can think of it as a rigid rod. So if you're standing on one side of the football stadium and I'm standing on the other, we're holding a rigid rod, let's say it doesn't bend or bow or anything like that, and I push it, you feel it the moment I start pushing it. And so now we got the issue is we know that sound takes some time to travel across the football field. Let's go out to I'm going to put you on one galaxy and I'll be on another. I'm going to get a rod connected to each other and I'm going to push it. At that point, you're feeling it before light has a chance to travel. Even if it takes a couple seconds for me to move my hand from here to here, it's going to take a few billion years for the light to ever get back to send it. So signals can be sent faster than the speed of light. That comes from Euler's laws of motion, which most people don't know of these laws of motion, but Euler was one of the greatest mathematicians of all time. And he speaks about how when things are attached and the effects that it has. So if you're attached to that force if you're attached to some body, or even if you're not attached, if you're on another galaxy and I take this long rod and I poke you in the head, you feel it faster than the speed of light. When that occurs, it's actually not faster than the speed of light. You can't think of it in terms of faster than the speed of light. It's instantaneously. And since it's instantaneously, you have energy that is not affected by time. Next slide. And we're talking about the motion, velocity over time, or velocity at a certain frequency. We take time, the factor of time out, and we still can have force. We can still have energy. It's not subject to time. So if I'm holding the rod again, then you're going to feel that force instantaneously. And I think that there are processes, which we'll get into. There's an example, a little apparatus I'm going to show you. I'm going to show you in a second where the force is 0 for a fraction of a second, and it's kind of a neat thing. All right, so because force can be transferred instantaneously, the rate of change of velocity will not change due to the said force, as time is not a factor anymore. It's canceled out. So there's other ways to send signals other than light and things that propagate over time. There are other methods. And so if you look at the way I do perpetual motion, and I hate to overuse this G because I used it as degeneracy factor before, let's call this gravitational acceleration, or let's just call it acceleration. Perpetual motion, in my mind, is acceleration converging to a steady velocity. And it does that as the force drops to 0. So that to me is perpetual motion. When you're going to get perpetual motion, it is the convergence of the force dropping off and acceleration decaying to velocity. Next slide. Okay. Here we go. Part 3. Let's get into, I'm going to show you, I got lots of little things. I'm hoping this slide is recorded because there's some other people I know that could not attend today that are going to watch this, and they're not going to see these the video so I did try to put some pictures in here. But the question, the table over here, you can't see it. I got like 10 different things on it I want to show you. All right, here's this. Here's one of the earlier concepts for perpetual motion. This is why people ridicule it, because these things don't work. But the question I raise is, does it not work because these people don't understand the laws of thermodynamics, or is it they don't work because they don't understand magnetism and gravity? Here's an example where somebody doesn't understand magnetism. So they have a ball at point E. It's a magnetic ball or a steel ball, and it is attracted to this other magnet or steel ball at A, and it goes up the incline. This is going to work just fine. But then when it gets to point B, this is a hole where it slides down this little chute due to the force of gravity and starts over and repeats. But anyone who's worked with magnets long enough is going to say that as it gets closer to the magnet, the force of magnetism is going to be stronger than gravity, and it will not fall into the hole. It's going to connect to the magnet. So this is a problem with an understanding of magnetism. No one put the equations down on paper and actually measured which is the greater force. And so a lot of these don't work simply because of engineering problems, not because they break any laws of nature, just because, well, they do break laws of nature. I mean, saying that gravity would be stronger than magnetism at this distance is not understanding laws of nature. But it has nothing to do with thermodynamics, nor a thermodynamic system. It's just a lack of understanding of how magnets work. Now, the most important thing I want to say for today, for this, before I get into it, is I believe that and I think I said it a little bit at the beginning, the study of perpetual motion is not only a good thing, because it has led to many inventions. I believe the compass was discovered while the guy was trying to figure it out how to, make his little perpetual motion machine. I have discovered many inventions, and I have 2 patents that actually went through and they've been accepted that they're very interesting new things to the world that I've discovered through investigating things that are impossible. I have to keep at the back of my mind that it is possible, even if it's not, because it keeps one pushing forward. Every time you have a perpetual motion machine fail, you go back, you look at it, you say, why did it fail? And if it's something that's new, has never been built before, and it failed, and you go and find out why it failed, then you know a little bit more about physics and nature than anyone else in the world, because it's a new aspect. It's a new invention. It's been done a different way. Even eddy currents. Most of the time, the equations known for eddy currents are so little known that we can only describe it in a couple areas. You have to approximate it when building your whatever, transformer or anything else. You kind of got to get in a ballpark and test it, based on the output. But there's no equation for all of the different forms of any invention we have that's to describe it. And so every time you have a perpetual motion machine fail, and you find out why it failed, then you know that much more about physics. So I believe that this is so important, that study, that I think it's not something that should be ridiculed. It's something that should be encouraged, knowing very well that it's going to fail, sure. How is it going to fail? We don't know. And then you never know, because I do believe that there is perpetual motion possible in nature, but you never know the one day when you don't know why, but it does work. And I think there's many examples of that. So people get into perpetual motion, they may build something, and it fails 1 or 2 times, and they quit. But Thomas Edison failed about 1,000 times, so he claims, on building his light bulb. And we need light bulbs, and we appreciate the amount of work he put in. But who else would pursue so long when everyone thought it was impossible? Flight, the Wright brothers, everyone thought was impossible. Not everyone, but most people thought it was impossible. And it's certainly very difficult. But my point is, it's a very simple problem, but it may take a very complex solution. There are many things that occur like that. Flight, it's a very simple problem, but it took a very complex solution. And now we have planes flying in the world. The light bulb as well. While there's only 4 components to a light bulb, it was a very, very complex solution to a simple problem. And I believe somewhere, and I believe that I've tapped into elements of it with some of the stuff I'm going to show you, that it's going to be possible, and I believe also it's something inevitable, that we will be able to represent the solar system on our table. Not with actual stars, but the mechanism. Let's give it a try. So let's go through. Next slide. Okay, so I have only ever had 2 patents awarded. I have filed numerous provisional, and then spent a year trying to see if there's a utility to it, and most of them I'm like, I wouldn't know how to make it into a product, so I let it expire. But the two actually have practical applications, and this one is the most fascinating to me. It is the simplest. It worked instantly the first time, and when I design around it and engineer around it, it works very easily and very consistently, and I know quite a lot about it. So it's the Zeta Pod. So I'll show a video in a second. May have to show you in a sec right now. So let me show you this image. All right, so what we have is a 2-inch outer diameter ring magnet right in the middle. It's going perpendicular. It's hard to see from this angle that it's actually a round magnet, but it is, and it's got a 1-inch diameter hole, and you have another magnet inside a little pod that has some bearings or wheels, so that it slides very easily through this tube. And in this position, and what we're looking at here, the magnet is in its resting position. It is locked in an offset position away from the magnet. So if you pull it down, it would pull back. If you push towards the center, it pushes away. So it holds it at this equilibrium point. Now, as you begin to press the magnet, the center magnet through, and you get beyond this threshold, a very interesting property happens. Well, it's expelled. It launches about 20 miles per hour, 25 miles per hour. There's a more interesting property is that when the pod locks into the magnet, the whole assembly will shake. So you'll feel it's got a significant amount of force, so you have equal but opposite reaction. However, when it comes past the magnet, you don't feel kickback. If you do feel any, it's minuscule. And I at first didn't understand why. This is considered inertial propulsion. Some people have theorized it. It does work. I have a prototype right here. All right, so this was I did get investment for this, and we didn't end up selling it. We did a Kickstarter campaign. I had presented to numerous conferences. So here's this. Oh, I don't know if you can see. Here's the Zeta Pod right here. It's got a magnet in it, and this assembly, it's got a little ramp, and you basically let go of it, and it locks right in. It just gets sucked in. Then I got a lever here, if everyone can see my video, and you turn it, and I'm going to try to catch it. I got videos of it. You turn the leverage very slowly, and it shoots out very quickly. Hold on, I got it. I'm going to shoot it over to this laundry thing. All right, ready? Everyone can see? I'm going to turn it. Did anyone see it? It shot across here. In any case, I got lots of videos online for this. Pretty simple. This is obviously not simple to make. This prototype cost about $6,000 to have built. But fortunately, the design was quite. It worked the first time. But I experimented with it and checked the math and everything. And I worked with another engineer, and we spent a lot of time to make sure that when this thing's built, it's going to work perfectly. And it did. And it's very nice. And you can actually shoot 2 of these little cars with each other. So that's the mechanism. The patent's been awarded. It wasn't believed. In fact, when we put it on Kickstarter, it's an interesting story. They didn't accept the project. And after about 14 days, I said, "Hey, you guys are going to have to accept this project, or now we're going to have some problem." And so what they did is they sent the attorney postmaster to my office to verify that it was real, because they were going to file as there is for using the mail system, fraud across the mail system, and their Kickstarter platform. So the post officer general came and he loved it. He's like, this is cool. This is cool. And so he went back and the Kickstarter approved the campaign the next day. I had that with the second patent with the patent office saying this won't work, it couldn't work. And my uncle, who's an attorney, and I were on the phone with them like, well, we'll just send you one. We got them working here, and we've already started selling them. We went to Indiegogo after the whole situation with Kickstarter. We stopped using them because of that nonsense. And so the patent office was like, really, it's working? Okay, then I guess it must work. I wouldn't know how. So the crank, the leverage, we use minimal amount of leverage to push that magnet through. Minimal. And you can do it very, very, very slowly. So what you do is basically you have a very small amount of kinetic energy to put it forward, a huge amount of kinetic or potential energy that equals the kinetic energy coming out. So it's the same energy going in as coming out, but it's different. It's you got your kinetic energy and potential energy put in, and then you have the kinetic energy coming out. But let's do next slide. I like the mechanism. So because the question is, when it is pressed out beyond this threshold, the magnetic field actually has to switch from repulsive to the other side of the magnet. In a fraction of a second, its value is 0. And at that point, the magnet is already accelerating. So it cannot give any force on the system at the moment, so it doesn't give any kickback. Now, that's a little bit confusing way of describing it, and it's not fully studied, but it's definitely, if you put this on the table and you lock it in, it's going to jiggle the whole thing. And when you turn it and shoot it, or you have a remote turn it and shoot it, it just doesn't kick back. You don't feel it. And it's minimal. You're reducing a little bit. But it's a significant and fascinating experiment that anyone can do. This is complicated. But you can go to Lowe's, which is the way I found it, and find these little tubes and do a similar apparatus and just press the magnet through, and that's how I originally started with it. And that costs just a few dollars that anyone can do. So the experiment is very easy to reproduce. The toy, of course, then it's a little more sophisticated. In any case, so since we can press this with leverage, and we can increase that leverage to the force of lifting a large 7-foot piece of metal with the pinky, then we don't really have much limit of how much we can amplify it. So kids can turn the Zeta launcher. Next slide. All right, so here's a kid loading it. And next slide. And that's my wife actually, and they're turning it, but it doesn't take much energy. You got leverage, working with you. And then the car zips out. So at this point, this is not free energy, nor is it perpetual motion, right? But what we're doing is we're getting the first component. We're having this increase of the field, and then it drops off to negative, and then the field comes in the opposite direction. Force. I have F, and it should be capital F for force. And that the direction is always going forward. So it's always positive. But the actual magnetic field does drop off for a fraction of a second. So at that point, the force is instantaneous, but the kickback is not. So you have this, I don't know, it's not a break of law of physics, but it's just a different way of looking at physics. So go ahead. Next slide. So can we expel it around a hula hoop? Yeah, I've done this. Thing shoots up in the air about 18 inches minimum. We have an 18-inch radius hula hoop. It's easily going to shoot around it. And what it's going to do is it's come to the bottom, and it's going to stop there at the bottom. It's going to go past it a little bit and rock, and then it's going to rest at the bottom. If we turn it on its side, yeah, it's probably going to come all the way around. And if it's really small loop, which I've done experiments, it comes all the way around. But depending on the size, it's going to start to slow down, and it may not come around. So let's improve that with this. Next slide. We got a spiral band. Now, I'm going to get the spiral band. Hold on one second.
Noise here. Okay, does someone need to be muted here?
The spiral band comes from, I'll probably see this, a number of patents that have been filed based on magnets. I have a bunch of magnets going around, if I would see my camera, going around this, where's my camera? You can't see the magnets in here, but where's the camera?
There you go.
There we go. Yeah, so it's kind of reversed for me. All right. So in there, a bunch of rod magnets and a spiral formation. Actually, mine's more of an elliptical orbit. I don't have a spiral because the spiral's already been done and it works for people. So they have taken spiral magnets and basically get the magnet moving all the way around a large ring and coming back to the beginning point and stopping, right? So that's the basis of it. I started working with spiral bands for a number of reasons, like sheet metal. So here's my, let's see if we can see it here. I got a magnet now around here, and I'm just going to twist it, and you see it's spinning in place. But if I had some friction, it would. Here's my. Try to get it on the camera. There we go. Let's see. Can't get it. There you go. You see it? I just kind of spins around, and then it goes back to its returning point. The bigger it is, the easier it is. Now, I use the spiral band for a number of reasons. I want it continuous. Or I can cut it. It's cheaper for one, and you can bend it. And here's the biggest reason: when assembling it, if you want to reposition it, you just bend it a little bit differently. And so here's what example. Hold on.
Jeff, could we move on to questions? It's moving on towards 4
So
o'clock.
I have.
Jeff,
My camera's
can
not
we
here.
move
There
on
you
to
go.
questions?
So I have
It's getting close to 12
some,
o'clock.
I don't know, some screws or bolts, and it braces the band in a curled motion. I'm not really seeing it good on the video. That's just one band in there, okay? And then the magnet on a bearing, it actually rotates. So, and this is going to be almost impossible to show on this video, but let me try, because I have to reach my hand in here, and I'm going to, no, I can't reach my hand in, there we go. Let's see, I'm going to get the camera.
Yeah, other way, Jeff.
Let's do this. There we go. And I change it, and I let go, and you see it pulls it to the band, the end of the band, and it stops, right? And so as it gets close, it pulls it to the end of the band or the middle, depending on how it's bent. So that's just one. It's not really, I'm not going to show. Or you can use levers, so that basically you have a band and an apparatus, and you can move the band to change the position. That's kind of useful too. Or you can simplify it, which is when you really get into the interesting aspects. I'm going to show you the next slide. So basically what you have is this spiral band. What it does is it's further away at the starting point. The launcher launches it forward. It then becomes attracted to the band, increases closer and closer and closer as it goes all the way around. It will not stop due to eddy currents, because even if you drop a magnet through a copper tube, it's going to keep going forward no matter how much it slows down. And then it will come to the end and then stop at its beginning point. So we have gone through a full circle without putting energy in. Now cycling, it's a little bit different. So then I thought, well, if I can do it with one band, all I need to do is get it to jump to the next band, and it's going to continue to loop. Spent 2 years trying to figure out if even that's possible. Sure enough, it is possible to cause it to jump to the other band. I will show you how. Hold on. All right, give me a second.
Okay, Jeff.
Yeah,
You hear me, Jeff?
I'm here. Barely.
So we're at about 15 minutes left in the conference. Just want to let you know. So
All right, I'll finish it up pretty quick.
It'll be a good choice either to finish your presentation or, take some questions?
All right, I'm gonna do it. I'm gonna finish in 5 minutes. I'll show you these things, and we're gonna do that. Okay, sorry. All right, so here's one where it's basically you got one band, if you can see the camera, and you release it, and it's hard to hold the level. Let me see if I can turn the camera a little bit. So, hey, that's not working. It basically would always go to one band and then stop, and I'm like, how do I get it off the band to the next? So I found a method is by putting them in an array that, sure enough, it does actually jump from one band to the next if you have a gap. I call it the band gap propulsion mechanism. It does work. Next slide, I'm going to show you, I got a video, I'm going to give you the video link so people can go see it actually working. So basically we can get it to the pod to jump off of the band onto the magnet to relaunch into the launcher. Next slide, please. So it's based on this concept here of Escher's vision of perpetual motion, where it appears as though they're constantly going up or down, but they still always go on a level surface. Basically what I've done is I've found a mechanism to do that with magnets, so the magnet field always feels it's rising or falling when it's actually just going in a straight line. And it goes at a continuous velocity. Next slide. So right here. So all we do is let go of it, and if it has enough energy to jump the first one, then it has enough to jump the next, and the next, and the next. I have not found a limit. I'm making one right now. It's 8 feet long. It just keeps going at a steady velocity, even if it's launched very slowly. You'll see that in the video. So I'm working on one right now. It's about 8 feet long. I think it was like 28 plates, and it just jumps from one to the next to the next. Now the question is, well, couldn't you put that in a circle? It gets complicated because then the magnetic field across is slowing it down. So the circle would have to be very big. But I'm not even working on that. I'm going to present this. Next thing, there's the image there, or the YouTube video link. If any of you want to quick write it down, I'll give it a second. And then I'm going to zip through the next slides and then answer any questions. Okay, we're going to go to the next slide. This will be recorded, so later you can check that YouTube video. All right, so we cut it back to the hula hoop. Next slide. And we should be able to turn the gears, or at least one gear, and to magnify the mechanical advantage. Next slide. And remember, it's going to have enough force because that spiral band is going to be pulling it constantly. Next slide. We can turn an axle and turn a wheel, multiply it. Next slide. And then you're going to have pods firing at different intervals, which is in turn turning it. None of this yet breaks any laws of physics. Would it work? Of course, no. It's going to fail, but it's probably going to fail on some engineering aspect because every component along the way works. And next slide. How much would we have to have that magnet turn that wheel? Only less than 3 degrees, which is about 2 centimeters, depending if it's like a 1 meter wheel. So if that magnet turning around there, 25 miles per hour, has enough force to turn another wheel 2 centimeters, then the whole system would repeat. Now, is it possible? I don't know. I just came up the other day just for fun, just to demonstrate that these things should be explored, because then you look at it and say, where's the error in this? Where's the mistake? What's not going to work? And then we understand a little bit more. Next slide. Here's some equations for all this. I've measured the mass and everything, and actually this is how we got the amount of force we would need to do it. We don't have time to go over this. It's okay. I'm going too long. Next slide. So essentially, would the cycle repeat? If so, it'd be perpetual motion. And if it would just fire all 7 pods, which that's been done, I've done that before, so then it's firing 7 pods over time. Then it's a semi-stable system. So and at that point, if it's semi-stable, then there's extra energy and so on and so forth. So I guess I'd like to just, we don't have a lot of time for questions. I'm sorry I went too long. I didn't realize. But I would like to see how these things don't work, and so that I can continue learning, and maybe you guys have some ideas, or maybe have some questions. So, I don't have a way to sum it up fast, but I want to cut it out now for time purposes. Does any other questions? Yes, yeah, thanks for copying that URL.
So, who has got questions?
So do you think that Peter Peregrine's perpetual motion machine would work?
Who's Perpetual Motion Machine?
Peter Peregrine, you know, he invented the perpetual motion machine in 1269.
I'm sorry, I don't know if any of those would work. I don't know, yeah, I don't know if any of those work. I don't know if they would work, I don't know if they're going to reproduce and do work. Oh, really? With the last one?
That's what you're doing.
Huh. Okay. Well, what part? With the band gap, the propulsion mechanism, with the link that Sam's requesting here? Or no, our pal requested? Which mechanism? I got three. I got it had the Zeta launcher, the spiral band, the band gaps. Which part do you think looks like his? No?
Now, I tried to look up your YouTube video. That link doesn't work.
Okay. Hold on.
I'm getting a black thing with an exclamation mark on it for the YouTube video.
Hold on one second. All right, hold on. I copied it, so let me just see what's up here. All right, let me see. All right, let me. When was the last time I sent that to somebody? All right, can you put the? Where's that link? I didn't hear. Oh, I see it. Hold on. Let me copy it.
Is there something we can search for in the search box that would find it?
No, unfortunately, I have to give it to you. It's unlisted. I'm trying on my computer to see why there.
Because I just get a black screen with an exclamation mark on it, and
I got it too. I got that too. Hold on.
It may be that unlisted causing it to be blocked.
No, I can't. No, I can't even get to it. Let me see if I have to. Oh, crud. All right, here's what I'm going to do. I'm going to copy this URL. I've sent it to other people, and they've seen it, so I know it works. All right, hold on. Let me log in to YouTube, my account, and I can go find it.
Well, let me see if I can. So some of your main points seem to be that like a perpetual motion machine does actually exist. That guy actually made one. That's kind of interesting.
What was that?
That someone actually appeared to have made a perpetual motion machine. Now, I generally consider your definition of perpetual motion is a bit different. I generally think that a perpetual motion machine just has to overcome all of its internal frictions in order to keep going continuously, which means it does have to generate a little bit more energy.
Well, that's actually kind of the same thing. If friction is a force, you're talking about is the force that puts it in motion greater than the sum of the forces. The sum of the forces would involve friction. So it's not just friction. You got other things. But that's kind of the same thing. It's just if you, I guess I never really thought of it until actually I had this band gap mechanism, and I see it's going at a steady velocity. But it's being pulled by magnetism. So that it should accelerate or slow down. But it's going across it at any length at a steady velocity. So I got looking at why would it do that at a steady velocity, and then I start looking at the what happens to when stuff's sending out to space. So I go study the Voyager 2, and it does seem that the acceleration converges to velocity. So I worked out the equations that came up with it.
Yeah,
now
there are a lot of equations there. So I'll have to admit I didn't understand any of it. But the main point of that was that you're saying that the dust wouldn't slow down Voyager, right?
Right.
So,
those are just small distortions or perturbations. It would eventually, it's a limit cycle, and it would lock back into its original course because the force wouldn't be enough. Now, if it hit, no, I mean, I don't know. I mean, we don't know because it depends. Is there a lot Is there a lot of dust out there, and is it all moving towards the Voyager 2? If it's not, I mean, because most of the dust out there, it's all moving somewhere. And I would believe that the dust would be moving away from the sun. If it's moving away from the sun, it's probably moving pretty fast. So the odds of it ever hitting any fragment of dust is pretty slim. That's, I mean, basically, how would the dust be there in the first place? And if it was, it would have to be moving somewhere. So is it moving in orbit around the sun? Is it moving to the sun, or is it moving toward?
How does equations? How the equations would show that there was insufficient force to cause it to slow down? Because intuitively, we know that it would. So, and equations don't cause forces. So, you'd have to overcome that intuition.
Okay. I think I know what you're saying. All right. Somebody's talking.
That's the Newtonian common sense in us. They're saying that if you got two things and they bash into each other, yeah, it's going to slow the other thing down. So, and I don't know that anything that
unless that there's another force, and I showed the force of the vacuum there. That the force is the vacuum is uniform in space. So I do believe this is a real field that has a pole.
I want to clarify that you think the vacuum has a force, because I've never heard of that. So
it was in my presentation.
I don't.
You don't know that you never heard that the vacuum field has a force?
Not one that can be.
We have to work it out of our equations. We have to work it out of engineering when you're designing very small, because the force becomes quite significant. So that's pretty much everyone. I mean, if you look anywhere on vacuum energy and vacuum field, it's basically the sum of all fields in space. So it has force. If it's a field of force, then it has force. What is its action? So what is it interacting? Every field is unique. The force is general. Every field is unique, and it interacts with unique action. So the electric field interacts with charge. The B field with charge per second with curl. So every field has a unique action. What would be the unique action that the vacuum field interacts with? This is my understanding is velocity itself. And because I took all the sum, it was a paper I wrote a long time ago for the MPA, is you took all the fields and you give it a constant value, and all of the fields, it's something that I can't show now, but basically it comes down to you can calculate the value of its action, and its action and amounting to the dimensions of meters per second. So it would be, you say that's a strange thing to interact with, but what it means is basically anything moving is interacting with the vacuum field. And since the vacuum field would be uniform in all space, it would have no direction. Since it has no direction, it has no curl. So it has no acceleration. So you can actually apply it to the equations, which you saw the equation there with the graph, and it does. So, sorry, go on.
Well, I mean, it's hard to extract motion out of that. I mean, it's like if you have a ball in the middle of a whole bunch of other balls hitting it every single side, then it's basically going to be a lot of energy there, but it's not going to move. There's no preferential. Exactly. You're right. Except that's exactly right. And that's my thought of it is that if it's everywhere, then it's not going to pull in any direction. Except that the velocity itself is already has a direction. So the body moving has the direction component, but the force would not change. Now, applying the equations I showed in that one graph, you see that the vacuum increases over time. The longer the longer it's moving, it has a longer interaction increase, but it doesn't increase like the other fields. It doesn't increase exponentially with distance, and it has no preferential pole. So it's simply interacting. It is the process that makes systems stable. So it's zero-point energy, and these fields are required for a system to even exist. So it is something that interacts with every field. And so it's just a matter of how. We're getting towards the end of our time here. So I just wanted to make sure, did anyone else have any questions they wanted to ask Jeff? Otherwise, I think we'll need to summarize here. So I'll give anyone a chance to ask questions to Jeff. Okay, well, I guess I gave people a chance to ask a question. So, Jeff, thank you very much for your presentation. And
right.
you know, it did run a little bit long, but I mean, I'll just summarize some of the kind of points that I saw
Sure.
in your talk, and you can I'll give you a final comment on those things. Like the things that I saw that were interesting is that there was actually a video of someone who seemingly created an actual perpetual motion machine that was gigantic. That was interesting, and it seemed to be emphasizing that your kind of perpetual motion is just like the motions of like the planets. Although that seems a lot like, you know, just Newton's law, once in motion, stays in motion. So that kind of conflicts with, I think, a lot of people's conceptions of perpetual motion. It was more like the big giant machine, which just keeps on moving, I think, rather than just a lack of kind of frictional forces. But you were trying to emphasize that things like Voyager 2, you know, can that be considered a perpetual motion machine? Will it eventually slow down? And you showed that, well, maybe it should slow down. Even the astrophysicists didn't know whether it, you know, eventually fall back in the sun if they thought about it long enough, I guess. Although you were trying to show through all this mathematical equations that there's not enough force there, and that you think probably Voyager 2 is going to keep on going, right?
Yeah, I'm pretty convinced, and I think it's going to converge to a steady velocity.
And let's see here. Another interesting point you made was that you think signals travel faster than light. Which I think
they can be. Not all signals do, but some can. A signal can be made to travel faster.
Between here and Alpha Centauri, if you pushed it, you're saying that should transfer instantaneously. I think some people would have a problem with that, but since I don't have a pipe to prove it with, then, you know.
Right.
But that's an interesting thought. I've never heard of that.
I've heard of that one before from others, actually.
You had this time crystal thing, which I thought was interesting. You said that this actually has been observed. That's something that's interesting. I also wondered, what did you think of, like, say, things like the drinking bird, which seems to exhibit perpetual motion, but that clearly extracts out heat energy from the environment. But it keeps going. So I'll let you.
That's interesting. Okay, so the drinking bird, yes, it's getting energy from something. So mine is that it's not getting energy from anything, and so the velocity would be constant with zero energy input. So the drinking bird would not qualify. Time crystals, you can go to Wikipedia. This is a fairly new thing, though they've been going back and forth. Somebody proposed it, and they said if this were possible and we can express it mathematically, then it would violate, you know, this and that. And one of the guys working on it is a Nobel laureate. So if you go to a Wikipedia article, you should be able to navigate to him and read more about that. I do not see much difference of Newton's first law of motion and perpetual motion. I don't see much difference. The divide, I don't think, is significant. When you think of vacuum energy as being something that interacts with velocity itself, that would help to explain things. There's also the fact that the universe is accelerating as the further it gets apart, or at least so it appears. I know some in here may disagree with that, but it does seem to be that as the universe expands, it is accelerating. And they call it dark matter or whatever else that is causing such acceleration. I call it the vacuum field is that extra force. As things get further and further apart, they're no longer being held back by the forces that which hold together, and then allows the vacuum field to have an advantage. Now at that point, you can accelerate. Yeah, there's time crystal article. So to me, if you think in terms of the vacuum field interacting with velocity, it's not much different or any less general than the gravitational field interacting with mass. It's basically acceleration interacting with mass. That's all gravity is. So whenever you take the action, and we can say the action of gravity would be acceleration, and the field itself would be mass times the field times the action is equal to force in newtons. And you can take that for any field, electric field, B field, and find its action, And if the product times the field equals force, and force is a general measurement, just like pressure. Other things that are unique are a resistance. Every action has unique resistor. So,
well, speaking of that, the other case I thought about was you've got superconductors. Now, there seemingly we have electrons in continuous motion without any input of energy.
Yeah, and then they're in their ground state, actually. So that's a lot of the interesting work with that. And of course, those doing the experiments are not talking about it because they want to keep getting funded and they don't want to be ridiculed. But there's a lot of interest in that with it, because you're now, when you do this, when you get something to its ground state, you're now able to extract those unique properties that occur there. And that's exactly the same thing. Sam, there is dark matter and there's dark energy. There's two different things. So that's essentially the same thing. You're basically opening up the ground state and making it larger, and you're able to interact with it at a hands-on level, and that is essentially superconductors. So we find this unique resistor and find a way to eliminate it, and then we got a lot of potential. So we find the unique resistor of the gravitational field, then we eliminate gravity. We know what the resistor is for electric field, which is, current density. So we eliminate that. We find a way to limit that or magnify what's against it, and we increase the field strength. So, or reduce it. We can then manipulate it. So it was of utmost importance for me to understand what is the vacuum field, what does it interact with, and how to resist it, how do we increase it. And what I came up with, and maybe someone will come up with something different, I'd love to see it, is that its action is velocity itself. Anything in motion interacts with it. And so then it starts to appear very general. It starts to look a lot like Newton's laws of motion, but I'd say it is involved. It is involved with his laws of motion. It is not something special or unique in the universe. It is commonplace. It is something present all around us. That's why I don't believe that perpetual motion is impossible. I believe it's commonplace. So we look at the stars and the moons rotating. That's perpetual motion as far as we're concerned. It's indefinite. We don't know when it's going to end. We can guess, but we don't know. An asteroid could come and explode into it and stop it from moving. And I've heard people say, well, the only reason things are in orbit in space is because there's no friction there. And I'm like, that's true. But we do a lot of equations studying escape velocity, everything in space, so we have to consider space. And most of space doesn't have an atmosphere. Most of it is freely, you can travel freely. So how do we operate in space? And how does the vacuum operate? So this is my interest, sir.
I think most people are interested in that guy who's offering the $10,000 award. What they're really looking for is something that can extract out additional energy. Because we all want. That's sad.
That's sad. For me, that's sad, and I don't like that personally. I believe it's fraud. Somebody that says that guy is fraudulent. If you say you want perpetual motion and then you start adding extra strings attached to it, that's fraud. It's rotten. Now, if that's everyone's expectation, that's why I'm doing this presentation, because I think we need to look at the two things as different. Because free energy involves a force being greater than zero and energy being greater than zero. And I don't see that with perpetual motion. I believe when you see the two combined, you're going to get a self-sustaining system with a half-life. So, temporary stable is not perpetual motion. That's exactly right. But you have perpetual motion and you have free energy. Free energy would be tapping into the stream, okay? But you actually, when you got the perpetual motion and you want to extract the energy, you're going to set a half-life onto the perpetual motion. There is perpetual motion, there is free energy, but they're not necessarily the same thing. So once you tap perpetual motion, which I believe exists, then it no longer is perpetual. Then the moment you plug into it, you start drawing a load, it's going to decline. That decline could be 1 billion years from now, but there's going to be a decline. But if you're not tapping into it, it could still be perpetual. It just doesn't have any load. So I see the two as different. And we don't have enough evidence showing that something can even keep moving and cycling on its own. and we get that, then we can find out how much load can we put on that so that it's reasonable to sustain it for some amount of time. So
Yep.
I'm interested in...
Get your difference,
Yeah.
what you're saying here with perpetual motion versus, harvesting energy from something.
Right. Two different things.
All right. Okay, well, Jeff, I think we're out of time here on our science conference.
Okay, thank you.
I thank you again, and if anyone else watching this video feels that they have a topic they would like to speak on this particular Saturday conference, we invite you to contact me, franklinwho@yahoo.com, and submit your topic, because we're actively looking for speakers to fill our schedule coming up. All right. So I'm gonna
Thank you, everyone.
and hopefully this will be